Hey guys, myself Tejas and I am studying in Sri Venkateshwara College of Engineering. Today let's discuss about classical free electron theory. Classical free electron theory. The classical free electron theory proposed by Drude and Lorentz modules electrons in a metal as free particles with no interaction among themselves. It assumes electrons move independently, experiencing occasional collisions with ions, causing resistivity. The theory explains electrical conductivity and Ohm's law but fails to account for phenomena like specific heat and the Hall effect quantity. Mechanics later supplied this theory, providing a more accurate description of electron behavior in materials. Classical free electron theory failed to explain specific heat of solids, temperature dependence of electrical conductivity, electron concentration depends of electrical conductivity. The first one is specific heat of solids. Classical free electron theory encounters a major failures when explaining the specific heat of solids. According to this theory, electrons contribute to specific heat only through their kinetic energy, predicting a specific heat that increases linearly with temperature. However, experimental observations reveal a discrepancy. Solids exhibit specific heat behaviors inconsistent with this linear prediction. Temperature dependence of electrical conductivity. Classical free electron theory explains the temperature dependence of electrical conductivity by assuming that electron is a metal behaves like a gas of non-interacting particles. As temperature increases, the average kinetic energy of this electron rises, leading to higher electron mobility and increases electrical conductivity. This theory predicts a linear relationship between conductivity and temperature. However, experimental observations reveal deviations from this linear trend in various materials. The third one is electron concentration dependence of electrical conductivity. Classical free electron theory postulates that the electrical conductivity of metals is primarily determined by the concentration of free electrons within the material. According to this theory, metals with higher electron concentrations should exhibit higher conductivity. However, this simplistic view encounters limitations as it fails to explain certain observations. In reality, the electron interactions and quantum effects play a crucial role, and the classical theory neglects these complexities. Assumptions of quantum free electron theory. Quantum mechanics. The theory relies on the principles of quantum mechanics to describe the behavior of electrons in a crystal lattice accurately. Periodic potential. It assumes that the crystal lattice imposes a periodic potential on electrons, forming energy bands. This periodicity arises from the arrangement of atoms in the crystal. Wave-particle duality. It considers electrons as both particles and waves, acknowledging the wave-like nature of electrons in the crystal lattice. Pauli's exclusion principle. This principle states that no two electrons in the system can have the same set of quantum numbers, accounting for the distinct energy levels and states of electrons in the crystal. Nearly free electron model. The theory assumes that electrons in a crystal experience periodic potential but are still essential free electrons moving in a modified potential field. This is a balance between the idealized free electron model and the realistic influence of the crystal lattice. The classical free electron theory makes several key assumptions and predictions regarding the behavior of electrons in a metal. Free movement. Electrons are considered free to move within the metal without significant interaction with each other or the atomic lattice. Drift velocity. The theory suggests that electrons subjected to an electric field will experience a constant drift velocity, contributing to electrical conductivity. Electron gas model. The electrons are treated as a gas with their behavior modeled based on classical statistical mechanics. Uniform energy levels. The theory assumes that electrons have uniform energy levels, forming an electron gas with a continuous distribution of energies. Fermi-Dirac distribution. The Fermi-Dirac distribution function is used to describe the probability of finding an electron at a particular energy level at an absolute zero temperature. Electron scattering. Collisions or scattering events between electrons and lattice ions are neglected or treated as infrequent. While the classical free electron theory is successful in explaining macroscopic properties like electrical conductivity, it fails to account for phenomena observed at low temperatures and on a microscopic scale. Quantum mechanics and more advanced models, such as the quantum theory of metals,